So we've said a fair bit about the golden ratio. Oh no, I've said too much. But we haven't yet said how it relates to the Fibonacci sequence. That's today's topic. In a minute we'll get the Code Goblin on to code some stuff up. But first, Chris is going to remind us what the Fibonacci sequence is. Thanks, Chris. Now you probably already know, but the Fibonacci sequence is when you start with 1 and then from then on you add the previous 2 times to get the next one. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. After that it gets a bit annoying to add up. So we can write that down in a more formalised way, that fk plus 1 is fk plus f of k minus 1. That's our occurrence relation for the Fibonacci sequence, and while we're at it we'll remind ourselves that a of k plus 1 is 1 plus 1 over a to the k. That's the recurrence relation form of the formula we use for the golden ratio in a previous video. So we want to look at the relationship between these two things. So we want to look at the ratio of successive Fibonacci numbers. Let's write out the Fibonacci's again. 1, 2, 3, 5, and then let's kind of stagger them. 1, 2, 3, let's put one more line in then, and 5, and then look at the ratios of successive terms. I've done it like this so that you can see how it's going to go. This one doesn't have a ratio, so we've got 1 over 1, 2 over 1, 3 over 2, 5 over 3, 8 over 5. And if we do the a terms, if we start with a1 equals 1, then a2 is 1 plus 1 over 1, which I think we can probably calculate as 2, and a3 is 1 plus 1 over 2, which we can probably see is 3 over 2. And you can see that these are matching up so far. This one is the same as that one, this one is the same as that one, and this one is the same as that one. But if we want to know if it continues like that, then it becomes quite annoying to actually do adding up. I don't like adding up. No one likes adding up. The Goblin hates adding up. But what he likes doing is getting computers to add up. So we're going to get the Goblin on to have the computer do the adding up, and then we'll see how he gets on with some of those examples, pushing this a little bit further with bigger numbers. Over to you, Goblin.
Thanks, Chris. I've got Python running in a Jupyter notebook. We're doing 21st century stuff today. No 1980s cosplay. Time for Goblin time. And this isn't a tutorial. I won't walk you through the code in detail. I'll mostly just show you what the code does. If you go to see an orchestra play a symphony, it doesn't come with a violin lesson, right? And neither does this. I can't even play violin. First, we paste in some baffling Goblin math code. Now we magically transform that into baffling equations for the Fibonacci sequence. Okay, these are the equations that we're used to. All it says there is that we start the sequence with 1 and 1, and that's A0 and A1. After that, every entry is the sum of the previous 2. And then instead of saying that in words, it says it in maths for some reason. Fine. Maths is stupid anyway. Let's set in code, like civilized goblins. We're using iterator Goblin style here, it's fine. We keep 2 entries from the sequence in A and B in that order, and every time we go around the loop we set the new B to be A plus B, and we set the new A to be the old B. This function returns an iterator, and the iterator generates an endless stream of values of the Fibonacci sequence, and that's what we want. Endless is too much though. We haven't got endless, we're a busy goblin, so we take a slice of that using itertools.islice, which is an iter tool that takes a slice. We take a slice with itertools.islice, which is an iter tool that takes a slice, and we turn that into a list so that we can see the answers. I'm pretty sure that 1 plus 1 is 2, and that 1 plus 2 is 3, and I think even that 2 plus 3 is 5. If you like, you can pause the video and add up the rest. I'm not going to. Goblins hate arithmetic. Stupid numbers. Now we actually want pairs of terms from this sequence to make our fractions with. You can see we've got the same numbers, but now they're coming out in pairs. We've got the 1 and the 1, followed by the 1 and the 2, followed by the 2 and the 3, and so on. This is exactly what we want, except it isn't exactly what we want, because it's come out with the smaller value first, and we want to take the fraction of the larger value divided by the smaller value. The latest version divided by the latest. And you can see it's done exactly what we want. It's grouped them into pairs with 1 and 1 together, and then 1 and 2 together, and then 2 and 3 together, and so on. And that's exactly what we want, except it isn't exactly what we want. We want them the other way around, because we want the latest entry in the sequence divided by the one before that, and these have come out the other way around from that. But it's okay, we'll fix that in post. There you go, we've fixed it in post. We've put the B and the A in that order in our fraction, and we've got fractions of this form. And we haven't seen the fraction class. Maybe you haven't seen the fraction class in Python before. I wonder if you can guess what it does. Let's do a quick example and see if anyone can guess what's happening with the fraction thing. So here I'm going to check that the fraction of 1, 2 is the same thing as 0.5, and the computer says it is. So the fractions are in fact doing what you think they would do. They're doing the fraction of the first integer divided by the second integer, but they keep it as a fraction so that we can have nice fractional results. Okay, that's all we need to get the successive fractions of the Fibonacci sequence in the form that we want. Now it's time to go back to our recurrence relation, which we'll first show in Goblin math mode. Okay, this is what we had, or what Chris had last time. And this is the equation we solved to get the numerical value of phi involving square roots, or the 1.6, whatever it was. And now we're going to consider successive terms if we treat this as a recurrence relation. So if we say we have a value of ak for some k, we make a new value by doing 1 plus 1 over the old value, and we start with 1 again. And there we have another list of fractions, and it looks like the fractions we had before, but we're not here to say that things look like. So what we're going to do is we're going to go back to the one we had before, give it a name, stored it in a variable, a fib is that, and then then it doesn't print it, so we're going to quickly adjust that. Let's go to the end of that line, turn, and then do a fib so that it prints it. Okay, that's printing. Now we're going to store this one in another variable. Let's call it a rec, and print that one. Okay, those are the things we said looked the same. One fraction of 1, 1, which is the same as the number 1. Fraction 2, 1, which is the same as the number fraction 2. Then we've got 1.5 and 5 over 3, which is 1 2/3. And let's go down, look down here. We've got the same thing so far, but we don't want to be comparing with our eyes. We're goblins. We want to make the computers do the work. So what we're going to do is the second one from a fib and the second one from a rec, and so on. And now you can see that they're side by side. They still look the same, but again, we're still not making the computer do enough of the work, so we'll keep pushing it a bit. Now we're going to make a list and say, well, instead of just zipping them, we're going to take the entries from the zip and say, are they equal? And the computer's going to say, it doesn't know what that means because we actually didn't use that name. Now if we use the name we did use, it says true, 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 but we want to kind of push the computer a little bit further to say, are all of these things true? I only want one answer. Are they all equal or not all equal? They are all equal, but I want the computer to say so. It doesn't count if I say so. Now the computer says so, and that's the end of that. You might be wondering, can we prove this in general, that the ratio of successive terms in the Fibonacci sequence is always equal to the successive terms in this recurrence relation derived from the continued fraction representation of the golden ratio? And the answer is yes, we can, but I'm not going to, because I'm a goblin and I don't do proving things. I'm going to leave that to Chris. So back to you, Chris.
Okay, thanks, Goblin. Now, to prove that this holds in general, it's not enough to keep making the computer do the work. We actually have to do some work ourselves by proving it mathematically. To do that, we're going to use a technique of mathematical induction.
But Chris, we only have a gas stove.
Mathematical induction is when we try to prove something for all n by saying that we assume it is true for k, and then we can show that it's true for k plus 1. And if we have that, and we can also show that it's true for n equals 1, then the rest of the numbers just follow from counting up from 1. You just go up the steps, 1, 2, 3, 4, 5, and it holds for all values. So we're going to try and do that with the relationship between our recurrence relation and the Fibonacci sequence. So let's assume that AK is equal to FK divided by FK minus 1, where the FKs are the Fibonacci numbers and the AKs are our successive terms in the iterative version of the thing that we know gives the golden ratio in the end. So if we have this to be true, then what does AK plus 1 equal? Well, it's 1 plus 1 over AK, which is 1 plus 1 over FK divided by FK minus 1. And I know a lot of students are very capable of handling fractions like this and getting the wrong answer, so we're going to be extremely careful. If you were a regional Olympiad candidate in your country, then you'll find this extremely slow and painful, but I don't care because I deal with people who weren't and they get it wrong. So we multiply the fraction by FK minus 1 divided by FK minus 1, which is the same thing as 1, so we're allowed to do that. Then on the bottom we'll cancel these, and the top we'll just put this there. So then we've got 1 plus FK minus 1 divided by FK, and we're going to do essentially the same thing again. We're going to write the 1 as FK divided by FK, which we are sure is 1, and then add FK minus 1, FK minus 1, oh, I can use an eraser there, FK minus 1 divided by FK, and then that's FK plus FK minus 1 divided by FK. And remember, our hypothesis was that the FK and the FK minus 1 are Fibonacci numbers, and we know that when we add two Fibonacci numbers from the sequence, then we get the next one. So we can write FK plus FK minus 1, we know that's FK plus 1 divided by FK. And so we have if AK is FK divided by FK minus 1, then AK plus 1 is equal to FK plus 1 divided by FK. So that's the first part of the induction hypothesis. And then we just need to check that we have a base case. So if we say A1 is 1, which it was, that's going to be our starting point. Then we want to compare that to f of 1 equals 1 and f of 0 equals 1. And that's why we have to start A with 1, because we have to use the matching k and the one before, and we have f0 and we don't have f minus 1, that's not a thing. So f1 divided by f0 is 1 is A1. So there's our base case, and it's going to work all the way through. So completely generally, the successive terms in our iteration formula for the golden ratio continued fraction thing are the ratios of successive terms of the Fibonacci sequence. And we're done. Well, are we done? We're kind of done. There's one thing we haven't proved here. We've proved that, let me get another piece of paper. As we continue taking terms in our continued fraction approximation, what we showed in the last episode was that A equals 1 plus 1 over A has a solution of the golden ratio. What we proved just now is that AK is the kth term in the Fibonacci sequence divided by the k minus 1th term. But what we haven't shown is that the formula AK plus 1 equals 1 over 1 plus A over k, we haven't shown that that converges to the limit of the golden ratio. I mean, it does, and it kind of obviously does, but if you're a sufficiently pedantic mathematician, you would say, and you'd be right, that we haven't proved that it does. And we're not going to. I'm not going to do that because that's actual work. Instead, I'm going to hand over to Chris for the sign-off.
Thanks, Chris. So that's all for now. Like and subscribe if you want more of these videos.
and don't if you don't. Unless and until then, ta-ta for now.